Okay. So we'll do the now exercise for this chapter number 6 here. It's very warm. Okay, so in the last 2-3 classes, we have learned how to derive the Gibbs energy for the solution, and then how to express Gibbs energy of the A, or when you have the AB solution, for example, how to express Gibbs energy of A inside of this solution. And that we call partial Gibbs energy of A in the solution, yeah? And so Gibbs energy of A in the solution was GI, so this is molar, this is per mole, is GI naught. This one is, this is what we have learned, yeah? And this activity coefficient is typically function of the composition and the temperature. And there's a very special case. One is Henrian solution. The other one is this case. And this means when xi become almost 0 and xi become almost 1. And in this case, gamma I equal to gamma I naught is constant. So this is only function of the temperature, independent of the composition. And in this case, this gamma I equal to almost 1. That's two special case. And then also we learn regular solution, ideal solution and regular solution. So when it's ideal solution, this gamma I equal to 1. So that's the ideal solution. Okay? So now let's try to actually apply this one in the real examples. Okay, let's look at question number 1. So we have CO2 gas is circulating slowly above the pure graphite at constant pressure at 1 atm at 900 degrees Celsius. The content of the gas, CO2, at the exit of this furnace is 2.95%. Okay? And then the rest of them is CO. So it's CO-CO2 mixture in the exhaust gas, and the content of CO2 is 2.95. And CO is, then 100 minus 2.95%. And if the mixture of the CO2 is circulating above the steel containing 0.6 weight percent of carbon at total pressure at 1 atm at same temperature 900 degrees Celsius, the steel will be decarburized if the concentration CO2 is more than 6.6. And then it will be carburized if the content is less than 6.66. And calculate the activity of the carbon of the steel containing 0.6 weight percent of carbon. It looks very complex here. Let's look at this. Whenever you see this kind of problem, any kind of problem you feel like it's very complex, try to draw the schematic diagram. That's always the very first thing you have to do. So this is chapter 7. Question number 1. So, one case, So I have CO gas is inserted, and this is pure graphite, solid. And graphite, I don't say that it's a solid, but I mean, the graphite, the melting temperature of graphite is about 3,000 degrees Celsius. So most of the case is solid state. And so if you blow the CO2, and the gas is coming out, the gas coming out is CO2 mixture. And this is 2.95%. And then, no, CO2 is 2.95. This is 97.05%. Okay. At T equal to 900 degrees, so this is 1173 Kelvin. Okay, so I'm adding this one, and then after reacting this one, it will produce this one. So it means, so this carbon and this gas is in equilibrium. Can you imagine this? So I'm adding this one, and by reacting this one and this one, it will produce this one. So it means this gas and the carbon is in equilibrium state. Okay? And P total, 1 atm. So it means I know the actual fraction of the gas, each gas phase. I know the total pressure, so it means I can calculate what's partial pressure of CO2 at 900 degrees Celsius against carbon. Okay. And the other one is, now I have another furnace here. I have steel, and this steel containing carbon, and the amount of carbon is 0.6%. Okay, so if you look at it, okay, so CO2 is circulating, so there's a CO and CO2 here in this furnace too. And if CO2 is more than 6.6%, then decarburization happening. And then if it's less than 6.6%, the carburization happening. So you have to understand first carburization and decarburization. So carburization means I'm injecting the carbon into the system. So in this case, the steel. So adding, so it means dissolving carbon to steel. So that's the actual meaning, carburization. Okay, decarburization means I'm removing the carbon from the steel. Okay. So we are using this kind of terminology a lot. Carburization, decarburization. Oxidation, deoxidation. Sulfurization, desulfurization. Okay, D means it's basically in reverse reaction, okay? So when this is 6.6%, yeah, 6.6% or above than this one, it will make carbon coming out. Okay? If this is less than 6.6%, it will actually insert carbon into the system. So I mean 6.6 is kind of the equilibrium state. Do you understand? So when this is 93.4%, so P total is again 1 atm, and T equal to 1173 Kelvin. So same condition, and this one and this one. When this is the gas, it will accumulate with the steel containing 0.6% of the carbon. Okay? And then the question is, okay, what is activity of the carbon when carbon content is 6.6%? Yeah? That's our question. Is it okay? At least, is it clear what is really actually what is really asked by the actual question here now? So now, if you do this, Now let's think about it, how to actually correlate this one. So this is one information, that is the other information. Typically, if you want to do any kind of thermodynamic calculation, we need Gibbs energy for chemical reaction. This is chemical reaction. But there's no Gibbs energy over the chemical reaction. But however, if you look at actually this information and this information, and both of them is CO, CO2, and carbon reaction. At this you can see that, yeah. And this actually, first part of the experiment can give you what's the Gibbs energy over the chemical reaction between carbon. So basically this one, if you just correlate these three, you can write down whatever chemical reaction you want as long as it contains these three species. Okay, the most obvious one we can think about is, okay, CO2 plus C equal to 2CO. Okay, so this is of course gas phase, and this is solid phase, and this is gas phase. And typically we need this kind of Gibbs energy to do any thermodynamic calculation, yeah? Is it okay? So let's take this one, delta G naught 1. Okay? And same thing for this one. So I have carbon, CO, CO2. Again, same thing. So CO gas, CO2 gas, plus carbon solid equal to 2CO gas phase. Now, you have to really now understand standard Gibbs energy and the activity difference. Okay? So this one, delta G naught 1. So when you write down this kind of chemical reaction, CO2 gas phase, carbon solid phase, and 2CO gas phase. Okay? So when you write down this one, the delta G naught 1 for this kind of chemical reaction, this one always assume that this is all the reactant and product is pure solid or pure liquid or pure gas phases. We don't know whether this is solution phase or not at this moment. All right? Whatever chemical reaction you are writing down, the chemical reaction, the reaction Gibbs energy, delta G naught, the standard reaction Gibbs energy, is assuming that all the component is the pure stoichiometric component, no solution. That's always starting point. And then, when you write down delta G equal to delta G naught plus RT ln something, that delta G containing some information about the solution because there's correction term RT ln something inside. That containing what's the solution property. So if it is stoichiometry, all this one is 0. And if it's solution phase, it's containing something inside there. Okay? So, by principle, thermodynamic equation, whatever thermodynamic equation you are doing, so when you actually apply your thermodynamic equation for any kind of application, okay, this is two different. Yeah? However, the thermodynamic equation itself is same. It means standard Gibbs energy is same. That's the starting point. But however, depending on your condition, you have to make a correction based on the condition, and that correction term is going inside of delta G. Delta G equal to delta G naught plus RT ln something. That's the correction term, depending on your condition. Okay? So, you have to really distinguish this one and the delta G. That's the very, very first thing, always. Okay. So, if you actually look at these two, so this one is same, basically. Standard Gibbs energy of formation, standard Gibbs energy of reaction, that's same value, yeah? So, if you look at this one, okay, delta G naught 1. So let's look at this condition and find out what's delta G naught 1. At equilibrium state, so it means my delta G equal to 0. So I'm talking about delta G in this case here. So whenever you have equilibrium condition, delta G is 0, not delta G naught. Then delta G naught, so then delta G equal to delta G naught plus RT ln equilibrium, yeah? Then this delta G equal to 0. So this one, delta G naught 1 equal to minus RT ln, in this case, CO2, CO2 and the carbon. So 2 moles partial pressure of CO square, and then partial pressure of CO2, and activity of carbon. Okay? And of course, this is 1, so this is only depending on CO, CO2. We know the value CO, CO2, yeah? So, I know the now standard Gibbs energy. So, this one, this part basically give you what's the standard Gibbs energy of the reaction. That's why it gives this information. And now, if you look at this one, then, okay, so same thing at equilibrium. So at equilibrium means this, and this gas is in equilibrium state right now, yeah? So if it is above this one, then there's chemical reaction happening. Below this one, there's chemical reaction happening. But when it's exactly at this one, it's equilibrium state. Yeah, there's no carbonization, no decarbonization, just stay as it is at this condition. Then at equilibrium, same thing, delta G equal to 0. So it means delta G naught 2 equal to minus RT ln now P CO square. And then this one, PCO2, and then activity of the carbon. And this activity of carbon is not 1, because this is solution. Carbon is not anymore pure carbon, yeah? It's a part of the steel, chemically bonded inside of steel. So it's a part of the solution, okay? And then now, delta G1, delta G2 is same, yeah? And then, from these two, we know that delta G naught 1 equal to delta G naught 2, yeah? So this part and this part should be same. Okay, for the first condition, CO2. So CO2. So if I write down this one, so inside of this one, and basically inside this one should be same, yeah? If these two is same, so it means the inside of long term should be same. Okay? So let's look at first part. PCO2 square. PCO2. So this one. And if this is partial pressure, this is percent. So you have to make this one as a fraction. And volume percent is volume. So this is volume percent. Okay? When you actually have the information of percentage of the gas phase, if there's no specific actually dimension about what's the exact unit, it means it's always volume percent. Because it's much easier to actually quantify the gas phase as a volume. Okay, not kilogram, not mass, it's volume. And volume percent is same as mole percent, yeah. So PO2 here is, so 0.9705 square. And then PCO2 is this one times total pressure. So partial pressure is 0.0295. Okay? Equal to this part. CO 0.934 square, 0.066 times A carbon. Okay, then you can get the activity of carbon. It clear enough? So don't be panic when you see the very wrong question. If you start to actually write down some schematic diagram, it's very easy in most of the case. Okay, and this process is really used in the industry. Really. So typically when you have steel, okay, we want to have the ductile enough so it can be moved, it can be actually deformable, but it is hard also on the surface. The most famous one to using this kind of technique is blade. If you have blade, typically one side is the very ductile and the other side is very, very hard. So when you have the blade or when you have a knife, so the edge of the way actually you are using to cut, that's very, very brittle but very, very hard. Very hard, but it's not ductile. So you can really cutting the actual your material, your food. But the other side, which we call the shoulder side, it should be ductile. If this entire thing is very brittle, then if you actually just, by mistake, if you just, just fell down the knife, it will just break down. Then you cannot use your knife. So one side, where actually you are cutting, is very, very hard. And typically, when you add more carbon, it becomes more harder. Okay, but it becomes brittle. And the other side is ductile. So you have less carbon. Okay? So how are we making it? So we make actually the entire thing, and then we just put this one, something cover here, and then on the one side, so here, initially, the carbon content, for example, 0.1% for all the steel. And then intentionally, we just add CO2 gas here, and then make carbon dissolve to the certain range here. And so the carbon content here becomes 0. For example, 5, 0.9, 1.0, whatever, depending on the temperature and depending on the time, how we actually do this treatment. Typically, when you have more CO gas, you have more carbon can be dissolved. Because the carbon activity should be higher, to actually dissolve carbon, the activity of carbon, virtual activity of carbon in the gas phase should be higher than the activity of carbon in your steel. Yeah. So in order to increase the virtual activity of the carbon in the gas phase, if you look at this, I have to increase this one, then this will increase simultaneously. Or if I decrease this one, this will increase. Yeah. So when you have low CO2, high CO, then your carbon activity is going up. Okay? So when you have the pure CO gas phase, for example, that have maximum carbon, activity, you can carry to the actual system. And then it can actually start dissolution of the carbon to the steel. While it losing the carbon, it produces CO2. Okay? So typically in the industry, people actually control this CO2 ratio to do this kind of treatment. Okay? So if you also think about the very old style of the sword making people, they they have the sword and they make initial sword, and then they just really, harden it by the hammer, and then they always put this one into the coal, into the coal. Coal is pure carbon, and there's this pure CO gas everywhere into this furnace. That's carburization process to make your sword more, more stronger, more brittle, more harder. Not brittle, actually more harder, There's actually the entire metallurgy of steel is actually hidden in the sword making actual process. Anyway, so that's exactly this process. And also in the other way, if you have the very high carbon steel, then I want to intentionally remove some of the carbon on the surface. Then you can do the decarburization. So it means you can add now huge amount of CO2 gas, then it will start to actually reduce the carbon to the gas phase, to producing more CO gas. Of course, you can inject the pure oxygen, then make also oxygen carbon reacting CO2, but if you add the oxygen, it will make oxide on the surface. FeO or Fe2O3 will be formed, so your decarburization process will be decreased, slow down. So it's better to use CO2 mixture to remove the carbon. Okay? You good? It's a very important process in the industry. Okay, let's look at second question. So now, okay, so we have the silver, okay, and then inside of silver we have the impurity called the kappa, Cu, and we are blowing the air into the silver bath, it's liquid silver, and to remove this Cu and Cu2O solid phase, okay. And if the reaction is carried out at 1000 degrees Celsius, okay, so what would be the minimum content of the kappa obtained in this process? So basically we have silver Ag and the Cu binary system, liquid state, and impurity is the kappa. And when you inject air, so oxygen, 0.21 atm, then the kappa in the liquid actually the silver, will react with oxygen to produce Cu2O. In this way, we can remove the certain amount of kappa from the silver. And then it asks, okay, what's the minimum content we can actually control? And activity Henleyan activity coefficient of kappa, gamma Cu naught equal to 3.54. So we have the Henleyan activity coefficient. So So it's air, so PO2 equal to 0.21 atm. Okay, and the chemical reaction we know is copper plus O2 liquid gas phase. And luckily we have the delta G naught of this reaction. Okay, so the copper is actually part of the solution, but we don't care whether silver is existing or not. Okay, however, the contribution of silver is actually coming here, Henleyan activity coefficient. So Henleyan activity coefficient is the interaction. It's determined by the interaction between your copper and the silver. Yeah, do you see what I mean? So Henleyan activity coefficient is active coefficient of copper when it is very, very dilute condition. Okay. When the surrounding atom is silver, this will be this value. When the surrounding atom will be gold, this should be different. Depending on the system by system, the Henleyan active coefficient for the same element should be different depending on the solution. Yeah, because Henleyan active coefficient is actually it can be determined from the interaction between the solute atom and the solvent atoms. Okay, so this is depending on the system by system, solution by solution. Okay, so, and however, this chemical reaction Gibbs energy is independent. As I mentioned, this is, when you write down this one, you don't know where you want to actually apply this one yet. Okay, this is just a pure copper oxygen reacting with a pure copper oxide. Okay, so when you do the reaction, you will form basically here Cu2O solid phase. This is the question. Okay, what will be the minimum copper content? This means, what's the equilibrium copper content here? Okay? So, at equilibrium, delta G should be 0, so it means delta G naught. So, activity okay, and this one so we know this value, we know the temperature, and this one, because there's no information, so we can assume that this is pure Cu2O can be formed because there's nothing else, and then partial pressure O2 equal to 0.21 and in root. So if you enter all this one, you can get what's the mole fraction of the copper. Is it okay? Good? So when I have this kind of question, then I'm always asking to the student again, okay, so you get actually answer will be like 0.0107. So it's about 1% impurity, yeah, still remaining in the silver. Okay? This is very cheap. Silver with 1% impurity is very cheap. So I want to decrease this one by 0.1%. Okay, one order lower. Okay, now it's 1% impurity. I will make this one 0.1% impurity. Then the silver price will going to increase. How can I do that? Any idea? So if you look at this chemical reaction, so if I'm hiring you in the industry, so I'm the boss, and I'm paying you, can you find a way to improve my process? I have to make more money, then I'll give you more incentive. Can you find actually a way how to improve this quality of the final product, silver? How can I do that? Increase partial pressure of oxygen. Yeah. If you increase this one, it will go more this way. So this will decrease. Yeah. I mean, if you look at this one, this is balanced. This is same value. You cannot change this one. So this is same value basically inside. So this total, the product here is same. If you increase this one, this should decrease. Yeah. So that's one way. And so typically, instead of using the air, they are adding enriched air. Enriched oxygen, enriched air, or pure oxygen. Pure oxygen is a little bit dangerous. But you can make easily, industrially, you can make easily about 36% or 40% of the O2 gas. That's easy to, and easy to handle too. So, by adding, for example, so it's in root, so it's like if you make twice of your partial pressure of oxygen, you get about 20% increase of your kappa, but this is square, so probably you can have the more impurity reduced than the 20%. That's the first one. And the other one? Any other method?
Removing the CO2.
How can I remove the CO2?
I don't know the exact way, but I think.
So, removing CO2 is very difficult, okay? Even you remove it, when you inject it, there's another solid will form, yeah? So it always makes equilibrium state, okay? But the other way is, activity equal to 1. Can I decrease the activity of this one? Less than 1. That's actually the thing. So if I add something on top here, which is not making actually any solution with this one, but some other impurity, I am intentionally adding something. We call this kind of thing as a flux, some agent to remove the impurity. So if I add some flux to make a chemical reaction with the CO2O, so for example, if I make more strong bonding with the CO2O, it means CO2 activity will decrease because of that. The same thing, yeah? So I make a solution phase or compound, solid, but activity of CO2 can decrease. Is that actually by the formation of some compound or solution? Okay? Then I can decrease this activity. So it means the chemical reaction going to the more forward reaction. So I can reduce the kappa. Is it okay? So this is the typical question you're going to see in your final exam. So you have something, and then after that, okay, find out better way to produce the better material. Is it okay? And then you can, of course, increase or decrease your temperature. Typically, decreasing temperature is very good. You don't need more money. Its energy cost is decreasing. But if you actually increase temperature, that's not very good merit, because you need more money to actually increase the temperature of system. Okay? Okay? Good. Let's look at next question. As I mentioned, now we have gold instead of silver. This is more expensive. So now I want to remove the copper from the gold, and okay, so PCO is now 1 atm. It's better than before. And the gold vessel is about 1,400 Kelvin, okay? And gold oxide is not stable, so it means typically it will produce the Cu2O or CuO, something like this. And now actually, copper oxide, there's two kinds of copper oxide in reality. CuO and Cu2O. In the previous question, I say it's Cu2O, so it's easy. We don't have to worry about two different kinds of oxide. But now, you have to even say, okay, whether it will produce CuO or Cu2O. Okay, and then based on that, what would be the minimum copper actually, solubility, copper actually the impurity we can control. Okay, it's a little bit more complex. It's one more complexity than the previous one. So how can we tell which product will be produced first? What's the atomic, what's the actually the, what's symbol for the gold? AU? AU? I'm thinking about platinum, sorry. AU, sorry. AU. And then we have copper, okay. And so Cu2O, either I can have Cu2O or CuO. We don't know this one yet, okay. And then I have PO2, 1 atm, and T equal to 1400 degree Kelvin. Okay, so I have two chemical reaction, 2Cu Cu2O minus 7, 3. Minus 35, 5, 6. And Henry active coefficient equal to 0.2. Okay. So first of all, which one will be produced? I think this is same question you actually dealt with for the iron oxide, FeO, Fe2O3, Fe3O4. Which one will be produced? So basically, we have to eliminate something and then to make chemical reaction between these two. And then we can tell, okay, which one, in thermodynamically, which one is the most stable? Whether delta G is going to the forward or backward. That will tell you which one will be produced, yeah? So in this case, okay, how can I eliminate it? So I can eliminate oxygen if you like. Okay, then you have activity of copper will remain in the end. Because copper will react with the Cu2 and CuO. Okay, so depending on what is my content of the copper, it could be different. But unfortunately, we don't know the copper content here. So if you eliminate the oxygen, it's a very difficult situation. And instead of that, if you eliminate the copper, then we have copper oxide and oxygen. So we know all of them. We know the partial pressure of PO2. And if it is formed, this is activity equal to 1, activity equal to 1. So we can really dictate which one will be produced from this condition. Do you understand what I mean? So instead of eliminating the oxygen, I'm eliminating copper here, okay? So minus 2. Then, so this will be 2CuO plus 2CuO minus 2 equal to Cu2O plus half mole of O2. Is it okay? This delta G naught equal to delta G naught 1 minus 2 times delta G naught 2. And this one is, okay, minus 70.1 and then minus, so this is minus 73.22 and minus 2, so plus, and 70, so 71.12. Okay, so this will be negative. Am I right? So it's a negative value. That's the only thing I need. So if it is negative, it means my chemical reaction is the forward reaction. Okay, so that means Cu2O is stable. Stable, then CuO solid. So this is now forming and this is forming. Okay? Yes, I mean, activity partial PO2 equal to 1. So everything, activity, all the activity equal to 1. So delta G naught equal to, delta G is, so you have to calculate delta G equal to delta G naught plus RT ln K, and this is 0 basically. So delta G is same as delta G naught. So delta G equal to negative. Not delta G naught, delta G equal to negative actually. And delta G naught is negative, so delta G equal to negative in this case. That's why it have the forward reaction. So instead of this one, this will be produced in this condition. So we know which product we'll have first. So we know that this is the product. And then now we have to really enter the partial pressure and then calculate the CU. So then, so next step, so now by using this first equation, we can do that equilibrium state. Delta G of reaction 1 equal to 0. So delta G not of reaction 1 yeah, and this activity in this case, activity coefficient and this is 0.2. It's very small, yeah, 0.2. It means you have very high mole fraction in the end. Yeah. So compared to the silver case, silver was 3.54, and then copper in the gold is 0.2. About 10 times smaller than the case for the silver. Okay? So activity coefficient is of the same element. Even you have the same element, depending on your solution phase, you can have completely different activity coefficient. Okay? Okay, let's move on to the question number 4. Well, before we actually move to the question number 4, then, I mean, copper, if you have copper, is there any other way to remove this actual impurity lower than 0.22? So let's assume the answer is 0.22. It's a huge amount of the impurity, yeah? Okay? So I have gold. Gold is very expensive. Copper is nothing compared to the gold. But I have 22% of impurity of the copper into the gold. So this is very cheap. So let's assume, okay, you are doing business. I'm the recycler of the cup to produce actually the gold. And I get actually this cheap gold. I actually improve the quality of this. And now, thermodynamically, if you have the gold and the copper, you have only 0.22%. You know, that's the minimum. 0.22 mole fraction. That's the minimum copper you can actually produce by assuming that you only produce Cu2O. Okay, and even you add 1 atm PO2. And one of these, you can increase your total pressure, for example. I mean 10 atm, 100 atm if you like. Then you can reduce a little bit further. Okay, that's one possible actually the choice you can think about. Because up to 100 atm, it's easy to increase the pressure, total pressure. And the other way is, I mean, in the real industrial way is, okay, the increasing the pressure have the certain actually the limit, but we want to typically produce the gold up to 0.00 or 0.99, or sorry, the gold actually the purity 99.9999, you know, something like this. Okay, at least 39.4959, about this range, and then you actually the gold price will increase drastically. So what people is really doing is, okay, so copper is the main impurity. And one of the things you can think about, okay, copper activity coefficient 0.2. Is there any way I can now change that activity coefficient? So you are adding intentionally some other impurity material into the liquid actually the gold. So is there anything which can change my activity coefficient? Hamilton activity coefficient. So Ag and Cu, Hamilton activity coefficient is 0.2. It means AgCu like each other. It's actually less than 1, so it's lower than 1, so it's the interaction between Ag and Cu is negative, yeah? So it actually attracts each other. That's why your non-active coefficient is lower than 1, okay? So if I intentionally add something which actually make this Henry activity coefficient going up, that will be very good. Okay? Or the other way around is, but when you add those kind of elements, you have to know that after removing the kappa, you have to remove that impurity too, yeah? The impurity you're adding. So you have to really think about something, okay, which can be also removable, easily removable after actually this treatment, yeah? After removing the kappa. So that's actually one candidate. The other candidate is, okay, so kappa, Au like each other, so it's negative. Then you can think about something like, okay, I add some element which make just the compound with the kappa in the liquid state. So make a solid kappa directly. Not pure solid, but Cu plus something else, making each other as a kind of compound, solid phase. Then it just precipitate in the liquid. Then you can just, remove all those actual solid particle. So then it means I'm adding some element which is more reactive than the gold. Okay? So if you look at Fay diagram, is there anything which make a very strong reaction with the kappa? So for example, zirconium. If you're adding zirconium and the kappa like each other. So then you can remove, by adding a couple of percent of zirconium, you can precipitate your kappa, a lot of the kappa. And then now you have some amount of zirconium into the gold phase, and you have to think about how to remove that, zirconium from the gold. I mean, for example, okay? That's not the solution, but I mean, you can think about something in this way too. Okay? So there's many different industrial way, and people still developing this kind of technology. Okay? That's the very standard technology. But because of in this day, we are doing a lot of the so-called CT mining. So in the past, we actually do the mining from the mountain, or, we really take out the mineral from the earth, and that actually has certain composition. Okay? So we developed certain actual technology to remove all the impurity inside of the gold based on those mineralogy of the gold. Okay? But now in this day, people just throw away all the electronic material, yeah? And all this electronic material containing very, very valuable metal inside. So all the plastic gone, everything, but inside there, you have silver, gold, platinum, and all kinds of the very, very rare metals. All the very actually the high purity or high valuable metal is inside of this electronic material. But now if you actually burn all this one, the mineralogy is completely different from the mineral which is coming from the nature. Okay? So you have to develop completely new process, new refining process. Okay? A lot of people doing this kind of project in this day. So in order to understand that, in order to find the way, you have to understand thermodynamics. So if you learn this course, you can start doing this kind of business. Okay, question number 4. Okay, now, so it's similar thing. Now we want to remove the lead from the silver base. Okay. So this is actually something which is just showing actually the concept I explained to you. Okay, so we have, we have to remove the silver from the lead, sorry. So we have lead, Pb, and we want to remove the silver from here. So silver is more expensive than the lead. So we want to collect the silver as much as possible in this case, yeah. And so at 500 degrees Celsius, and in order to actually remove the silver, we are adding Zn, zinc. Zinc into the here, and then solid compound, Ag2Zn3. So because zinc like Ag very much, so it actually formed the solid phase instead of liquid state. Okay, and then it formed solid, and then it will be floating on top of the lead because lead is so heavy. So actually solid phase is just floating on the liquid phase, on top of liquid phase, and then you can just skimming out, and then take all the silver out of the actually your lead. Okay, and calculate the amount of silver in the liquid lead, and after equilibrium, and after the desilverization process, and after desilverizing process, so it's removing the silver, the Z10, the mole fraction of Z10 in the lead is 0.0146%, or mole fraction. This is real industrial process. So if you go to the Korean zinc, Korea iron in Ulsan, they are using this process. Korea zinc. Okay. So we have liquid PB, and here we have silver as impurity, and we're injecting Z10, and then by reacting these two, three solid is forming, and this temperature 500 degrees Celsius. Okay, and mole fraction, so Henry active coefficient of Z10 equal to 11, and active coefficient of the Ag, silver, equal to 2.027. And then the chemical reaction, Ag, okay, so, and then final mole fraction of Z10, 0.0146. So we can add more Z10, but I mean, if you add more and more, it's also difficult to remove more and more. So we want to control this final, actually the zinc content is 0.0146 mole fraction. Okay, so from this chemical reaction, this is, if you look at this one, it's minus 127.6 kilojoule. So the whole idea is, okay, if I want to make this making this one, so basically we have to find what would be this. Okay, so if you are designing the new process, think about it. I have this one, the active coefficient is only this one, so even by injecting the oxygen, it's impossible because silver is very stable, it's noble, so you cannot make oxide here, Ag2O. It's very difficult to produce it. So if you're injecting oxygen, lead will become oxide first. That's one way, if you like. You make everything oxide, all the lead oxide, and then you collect it, and then you reduce it again. It's a very stupid idea, but that's one way. And however, if you want to just remove the silver as it is, then you can think about, okay, I want to add something. And that something which is added into the liquid of lead should react very quickly and produce as much as possible new solid phase or new liquid phase, which is separatable from the liquid lead. Okay, that's the idea. So people are actually looking for a lot of thermodynamic information and then find out, okay, this one, first of all, at this temperature, make solid phase. And if you look at Gibbs energy, it's very negative. So it means it's a good sign. It doesn't guarantee that it will produce this one. However, if it's more and more negative, you will have more chance to make a more solid phase, yeah? Because chemical reaction is determined by delta G, not delta G naught. However, delta G equal to delta G naught plus something. So if your delta G naught is negative, it means your chemical reaction, delta G, have more chance to be more negative. Yeah, so it's a good sign. So people using that. And then, the other very interesting story behind here is, okay, so in the end, this one, at the equilibrium state, my delta G equal to 0, and that's the actual final state. So delta G naught and this one is activity coefficient, mole fraction, and this one same thing. If I found some element which have very high activity coefficient in the system, so if this have the very high activity coefficient, okay, I'm adding 1% for each different one, but among them, which have the highest activity coefficient one, will have highest activity in the end. It will produce more this way. It will move this chemical reaction more to the left to the right side, yeah? You have high chemical reaction, high activity means I have more energy and pushing down to the actually the other way. Okay? So when you have a high activity coefficient, and this is 1, this is determined, you cannot change it. So if you're adding same amount, but if this activities become bigger and bigger, your final content of the AG should be smaller and smaller. You get it? So locally, the ZN, the activity coefficient is 11, even 11 in the lead base. So it's one of the best agent you can actually think about. Okay? It's a design concept. All this one is behind in the actual this development of this process in this way. Okay? And so we know this value, we know this, and we know the other one, so we can calculate mole fraction of the silver remaining in the liquid base. Okay? Once you take out Ag2 Zn3, then you remelted it. You're melting it again. And then Zn have very high vapor pressure. So if you increase temperature, Zn will be evaporated by itself. So you get actually silver, high quality silver, easily in the end. Okay? And also, if you're adding oxygen, Zn will like to form the oxide too. So it's easy too. Okie dokie, good. Let's move on. So it's next question basically. So unfortunately we know that final Zn content is about 1%, and this is not good. We have to remove this one. Yeah? So that's the question here. So this is subsequent actually the process than this one. So remove the silver from the lead, we add actually the Zn, zinc, and now it results to liquid phase, and then almost all the Ag go to the phase Zn and being thrown out, so we remove it basically. And now there's the dilute solution of Zn into the lead. So we have about this amount is left over, and then to remove the Zn, we blow the Cl2 gas. Okay, so chlorine gas, Cl2 gas, and then probably chlorine gas will react with the lead or Zn, produced PbCl2 or ZnCl2, something like this, yeah. And so if you do that, so it will produce liquid ZnCl2, and this process is also produce PbCl2, and so it will eventually form the ZnCl2 and PbCl2 solution. And we need to stop the process at a certain moment to avoid excessive loss of the lead. Because if you're adding more and more chlorine, it will produce all the lead become lead chloride. Then, I mean, you are purifying it, but actually you are losing your resources simultaneously. So we have to stop at a certain point. Assuming that we stop the process when mole fraction of PbCl2 in the chloride solution equal to 0.01, and calculate the mole fraction of Zn in the lead at this condition, assuming that this PbCl2, ZnCl2 is ideal solution, and the reaction is carried out at 400 degrees Celsius. So it's a little bit long, but I mean the idea is very simple. Basically, what we are learning right now is all Henrian solution. Okay, we are using Henrian active coefficient and etc. So this is number 5. So basically, we are producing so we inject Cl2 gas, and eventually this will be produced in the equilibrium state. And this one, mole fraction, 0.01. That's the final state we want to actually arrive, okay? And this is also ideal solution. That's what it said. And this one, we didn't say it's ideal solution yet. And if you look at it, activity, Zn equal to 27. And T equal to 400 degrees Celsius, so it's 673 Kelvin. So it's a different temperature. Yeah? So previously it's a 500 degrees Celsius, now it's a 400 degrees Celsius. You see, activity coefficient is changing with the temperature even. Yeah, Henrian activity coefficient is changing. So we are on the what is last. So this mole fraction of Zn, how much we can reduce? That's the actual question. Okay, the information we have, PB, and this is liquid. Okay, eventually we want to make this one 0.01 mole fraction. So it means this mole fraction is 0.99. Ideal solution. So it means activity of this one is directly connected to the actually your mole fraction. Yeah, that's the ideal solution. Okay, and then we know Zn activity coefficient is given, and under this condition we want to know what's the final Zn solubility. Okay, so just think about this one. I think you can probably think about already using this one. So we want to know what's the limit of Zn, what's solubility of Zn under this condition. And I know the activity of this one because it's 0.99. Ideal solution. So mole fraction is same as activity. Okay? And I know the activity coefficient, and I want to know the mole fraction. But in order to solve this one, in order to use this one, you need the Cl2 gas pressure. But we don't know the Cl2 gas pressure. But the other way, I mean, we have this equation now. Okay, I know the activity coefficient. I know the activity of this one. This one, I don't know. However, this is dilute solution. So this is very enriched solution. Solute, solvent. Solvent, Gaussian solution. Gaussian solution, same as the mole fraction. Yeah. Gaussian active coefficient equal to 1. So PB lead activity, PB liquid activity is same as mole fraction of PB. We know that this is very small. So mole fraction of this one is almost 1. We can assume that. Okay. So it's 1. This is 0.01. And we can calculate Cl2. Is it okay? So we calculate PCl2, and we enter here, we solve this one. Or we just combine together and remove the Cl2, because we know this one, we know this one, we know this one, we don't know this one. That's also another way. There's two ways, yeah? You get it? So the first one, if you want to, you can actually use. So first method, you calculate this one, PCl2. So delta G of reaction equal to 1 equal to 0. So delta G naught of reaction 1. Okay, so this is almost 1. As I mentioned, this is Laurentian solution. If you like, 1 minus x, if you like. X is now Zn content, but you can assume in this way. Or, if you want to really do it, 1 minus x Zn, if you like. That's also another way. Okay? And then this one, now, so, in this case, we can assume this way. It's easy. Otherwise, we cannot solve the question. And this is activity coefficient of PbCl2 times mole fraction. And this is 0.01, and this is 1 because of the ideal solution. Yeah? Then, from this, we can calculate PCl2 equilibrium gas pressure. Okay? And then, you can use this one to the second one. Delta G of reaction 2 equal to 0. So it means delta G naught of reaction 2 equal to minus RT ln. Now, same thing, activity of Zn, Cl2, activity of Zn, and PCl2. And this PCl2 should enter here. And then this is active coefficient of Zn times mole fraction of Zn, and then this is 0.99. Similarly, yeah. So you get actually the xZn. So this is the first way, and second way is more easier. You combine these two together, remove the chlorine gas, then. Okay, then delta G of this reaction equal to 0 at the equilibrium state. So delta G naught 1 minus delta G naught 2 equal to minus RT ln equilibrium constant. And this one is minus RT ln. So activity of PbCl2 and activity of Zn, activity of Pb, activity of Zn, Cl2. This one, 0.01, 0.99. This one, active coefficient of Zn times mole fraction of Zn. This one, theoretically, 1 minus mole fraction of Zn. So you have only one variable in the equation. And because this is nearly 0, so you can assume it's almost 1, and then you get only xZn directly, if you like. It's up to you, but you can assume 0, and then do it, and then you just confirm that, okay, xZn is really small, then that assumption is okay. The first assumption is okay. Okay? So eventually, if you learn actually all this activity concept, what you have done in the midterm number 1 is meaningless, because that's part of this one. Yeah? And some case we assume the activity equal to 1. Some case we assume that this is part of the solution. And so we actually all this actual activity concept encompass what you have learned in the before the midterm number 1. Okay? So in the midterm, so we can make exactly same type of the exam as midterm number 1, but we change all this one instead of pure solid phase or pure liquid phase. We assume all this one is part of solution. Then it make another completely different actual story. Okay? So we'll continue a little bit of this one next class. Okay, any question? No? No question all the time. Good. See you on Wednesday.